RISC-V processors against a formal version of the instruction set architecture specification. But first, let's talk a little bit about what RISC-V actually is. So RISC-V is an open instruction set architecture that can be freely used by anyone for any purpose. But it's not, and this is the important point, it's not a processor. There are many processors out there that implement the RISC-V instruction set architecture. And of course, in order for the RISC-V project to be successful, we need to make sure that all those different cores are actually compatible with each other, so that all these cores actually implement the same ISA specification and implement it correctly. And my hope is that with my project, riscv-formal, I can help achieving that goal. So then I have a quick introductory slide about hardware model checking. So when we do hardware model checking, we're looking at the following problem. We have a circuit, then we have an initial state for that circuit, or a set of initial states for that circuit. Then we have a set of assumptions. And now we would like to know if certain bad states can be reached from those sets of initial states. And if this is possible, if we can reach a bad state from the initial state, then we have a bug. And we would like to see a counter example, like a simulation trace, that demonstrates that actually this bad state is reachable from one of those initial states. And this part of hardware model checking is called checking of safety properties. Another part of hardware model checking is checking for liveness properties. And liveness properties means checking that a good thing that we want to happen is bound to eventually happen, and that there is no way for the circuit to somehow get stuck or freeze, and therefore it will never reach this good state. However, in this presentation, we will look pretty much exclusively at safety properties. But I think it's important that you know that safety properties is not everything in hardware model checking. There's another aspect to it as well. When we are looking at safety properties, we can look at them in two different ways. We can do a bounded or an unbounded check. And a bounded check simply means that we do not consider traces that are longer than some predetermined natural number. So maybe we say we have a bounded check of depth 10. Then we are only interested in traces that can reach a bad state from an initial state within 10 time steps. Of course, in many cases, this is not sufficient. So maybe we need a higher bound, and we say, okay, can we reach a bad state within 50 cycles or something like that? But in many cases, we don't want any bound at all, and then we call this unbounded model checking. And if an unbounded model check succeeds, this means that we can be sure that no matter how long you will run your circuit, it will never be able to reach one of those bad states. However, for many real-world problems, unbounded checks are hard to finish. Therefore, in many cases, a bounded check must suffice. With processors, for example, when you look at the processor, then in many cases you can say, okay, within a bound of that many cycles, you can pretty much reach any state the processor could reach. And there are some methods, I will talk about this at the end of the presentation, to raise your confidence level that your bound is actually sufficient. And in this presentation, we are looking primarily at these bounded checks. The checks that I will show you, in principle, they would also work with unbounded model checking. But for many processors, this is not really something that's achievable at the moment with the current tools for this kind of proofs. So you need tools to do that, and there are two options. You can buy one of the commercial tools. They are pretty prohibitively priced, so you need deep pockets. And at least in my experience, it's also not so easy to get access to those tools when you're at the university. Which is different from, for example, synthesis tools that are also very, very expensive. But if you're at a university, then usually you can get access to them. Or you use the free and open source tools that I wrote. And of course, they are the default option for riscv-formal. I just want you to know that the checks that I'm talking about here, that I'm showing you, they are not limited to my tools. And if you already have like one of the commercial tools, then you can also use those tools with these checks. So this is model checking. But we would like to look at a very specific kind of model check, something that is called end-to-end verification. And end-to-end verification simply means that we look at the circuit as a whole, and we have a property that describes something that the circuit should do as a whole. As opposed to, we could also just break our circuit down into smaller circuits and then have smaller properties for each and every one of them. So for example, when you have a processor, somewhere in there you have an ALU, and then you can write properties, how should this ALU behave? And then you take another component and you write properties, how this other component behaves. There are a couple of problems with that. The first problem is, if you do that, then your properties are not portable to other implementations. Because if you look at this different RISC-V processor, this different RISC-V processor will use different internal interfaces. Its ALU will work differently and stuff like that. So you can't take the properties you've written for one processor and port them to the other one. The next one is, the next problem with not end-to-end verification is that that you have to look at the properties for these individual components, and then you have to argue yourself how these properties you wrote for the individual components are equivalent to a set of properties that would describe the overall behavior of the circuit that is desired. If we do end-to-end verification, then we solve both of these issues, but we have a new problem. Now we have a larger circuit and more complex properties, so maybe we run into a dead end, and we have something that would in theory describe the behavior we want from our circuit, but there is no practical way to actually run the proof. However, in the last decade or so, the solvers have improved immensely, and because of that, we can now do end-to-end verification for some kinds of circuits and some kinds of properties. Sometimes you have to be a little bit creative how we get to the point where we have proofs that actually work. But we can now do things that were completely unthinkable 10 years ago. And of course, because I wrote these tools for model checking, I wanted to have a demo project that I can show people and can demonstrate that with my tools, you can actually do non-trivial, very complex things, even things that many people would still believe are not possible to do with formal verification. Okay, so that project, of course, is riscv-formal. And it's a framework for end-to-end verification of RISC-V processors. It's not a formally verified RISC-V core. So when you Google for terms like RISC-V formal verification, you will find that there are a couple of formally verified cores out there. But those proofs are not portable to other cores. So if you have already written a processor, and you have written it in Verilog, and you have your priorities were to make it really, really small or really, really fast or whatever, you can't just take one of those proofs and apply it to your processor. However, with riscv-formal, we have this kind of universal framework that can be applied to at least in theory, all RISC-V processors out there. They just need to implement these things here. So first, we need to add an additional port to the core, the RVFI, RISC-V-formal interface trace port. This is something that's usually done as like an optional feature that you can configure to be enabled or disabled. And then you formally verify the version of your core with this trace port enabled. And if you are not really sure if the version of your core with the trace port enabled is equivalent to the version of the core with the trace port disabled, well, formal equivalence checking is another part of formal verification, and you can use it here to make sure that you haven't like accidentally fixed the bug by adding the trace port here. And then you need to tell the RISC-V-formal framework a couple of things about your processor. So for example, this RVFI interface has a couple of channels, so you can retire more than one instruction in each cycle, and you need to tell RISC-V-formal how many channels you have. You have to tell RISC-V-formal which ISA you're implementing, so it's 32-bit or 64-bit with compressed instructions enabled or not enabled, and some other things like if the core will trap on a misaligned load store or not, because the RISC-V specification essentially allows you to write to implement a core that does not allow misaligned loads and store on the machine level, but instead implements them using some kind of trap handler. And because we are not really taking this software components like the trap handler that implements misaligned load store into consideration, we have to add this here as an additional configuration flag. Okay, so how does this interface look like? It's an output-only interfaces. So these are the ports that you need to add to your processor. All of them are outputs. And nret is just the number of channels you have. So for each channel, we have a valid signal. If it's high, then we retire an instruction via this trace port in this cycle. And if it's low, then we don't. That's just the index of an instruction. I'm actually thinking about when I refactor things the next time to rename this to RVFI index instead of RVFI order. Then the actual instruction that you retire, 3 flags that tell us, did we trap on this instruction? Is this the last instruction in the stream? So we don't expect the next instruction to be retired. And is this the first instruction of an interrupt service routine? And then we have a couple of details about the instruction that we just have retired, like when you have source registers, the register address of RS1 and RS2, and the data that we have read from that registers. And if you have a destination register, then the address of this destination address and the data that we have written there, the address of this instruction, the program counter when we start executing the instruction, and the address of the next instruction to be executed, or the program counter after we have executed this instruction, and so on. Yeah, so one thing that you might notice here is that there's some redundancy in there. Because, for example, the register indices for the source registers are also encoded, of course, in the instruction word. But as you will see later, there are a couple of proofs that we run here. And there will be one proof that checks if this instruction, for example, matches the register numbers we have here. Then another proof that just uses this register numbers here and the read and write data to see if this stream of instructions is actually consistent with an actual register file that remembers the value written to it. And because of that, and because maybe we can make it so that this is a more or less direct connection from the register file, we will get a much easier proof for this second step compared to if we would have to decode the instruction again. Okay, so I've hinted already a little bit on this slide now, the verification strategy. We have 2 different kinds of checks that we run here. We have instruction checks. This is one formal proof that runs for each instruction and each value. So if your ISA has 50 instructions, we have 2 channels. This alone 100 checks that will run. That can also be a good news that there are so many checks, because it means you will be able to utilize all the cores that you have lying around, because most of the formal programs are actually single-threaded. It's very hard to parallelize that. But when we have 100 independent proofs, we can utilize 100 cores on your Amazon cloud or whatever. So with the instruction checks, we look at the instruction word, and then we look at the data read from the register file, the data written to the register file, and if this matches the operation that was encoded in the instruction. Usually, if we make an error, if we misread the specification, and we accidentally implement an incorrect behavior for one instruction, then usually this check will just fail for that instruction. But even if all of those checks succeed, we haven't proven yet that the processor is really matching the ISA specification, because when we output here that we have written the value 50 to register 12, maybe the core lies. Maybe a read in the next instruction that reads from the same register will read a different value. That could be because there is a bypassing error, for example. So we need another check, list of checks, another set of checks that check if this stream is actually consistent with stuff like the register file. So this is what the instruction checks themselves look like. So we have a checker that has all the RVFI signals as input ports, so we can hook it up to our processor. And then an additional 1-bit check input. And we just construct a bounded model check for n cycles. And in the first cycle, we reset the core or whatever, and then we run it for maybe 50 cycles. And in the 50th cycle, we assume we retire an instruction, namely the instruction we are checking in this one check. And then we assert that the behavior is correct, that if it's an XOR instruction, that really the data we have read from the register, XOR is the register value we have written to the target register, that the register addresses are all correct, stuff like that. And we do this for each channel and each port. Compressed instructions are treated here as separate instructions. So a C add I and an add I are two completely independent things for riscv-formal. And the same thing for fused instructions. So if you have support for fused instructions in your core with regard to riscv-formal, that's just another instruction that happens to belong that's supported by your core. And if you check out riscv-formal and look into the instance directory, then you can see all these individual instruction models. So just as an example, here we have the instruction model for the add E instruction. That's what the models look like. It's not really the checker. The checker is in between in the design hierarchy. So we have some input ports that you might recognize from the list of RVFI ports we've seen before. And then we have some output ports, and those are the specified behavior given those input signals. And then the checker will check if this spec signals actually match the other RVFI signals that the checker has seen. So that's the interface. All instruction models use the same interface here. And then whatever the instruction is, in this case, it's an I-type instruction format. So we take the instruction and we decode it so that we have it in different signals. And then we say, OK, it's an add E instruction. So we have to take the read data from source register 1, and we add the immediate, so we get the result, things like that. And you can see this is actually a very, very simple description. It's not like black magic. And that's the whole idea here. We take this big property, conforms to ISA specification, and we break it down into a large list of small properties that each individually can be checked, even though the core itself is rather large. So the consistency checks, they look very similar to the instruction checks, at least from the interface. They also have the signals, the RVFI signals. We not only have a check signal, but also a reset signal. And the reset signal essentially disables the checker for the first n cycles. And so for the first n cycles, we have reset active. And then we have m cycles where reset is inactive. And then the last of those m cycles, we also write the check input. And we only consider in this checker stuff that happens during the second period, the m cycles we have at the end. Because we might need something like 50 cycles depth for our bounded model check, so that the core can get into all the relevant states that might be interesting. But we can't prove that we are consistency, for example, with respect to the register file for all 50 cycles. That's too large, that's too complicated. So we only look at the instructions retired in the last 10 steps of those 50 cycles. And we only say, OK, if there was a write there, then this much must match a read in the last cycle where check is active. So with both kinds of checkers, the instruction checkers and the consistency checkers, if they fail, we get a counterexample where in the very last cycle that we have configured here, something happens that violates my description of what is the expected behavior. Some of those consistency checkers have an additional trigger input that must be asserted somewhere within this m cycle period. Liveness is one of them. We will. Oh, it's on the next slide. So these are some of the consistency checkers that we have. So we want to make sure that we retire one instruction that has index k, and then we retire another instruction with index k plus 1, that the next program counter from instruction k matches the program counter from the instruction k plus 1. However, the instructions might be reordered. So it's possible that the k plus 1 instructions is retired later, or it can be retired earlier. And in this case, we just handle that with two different checks. So the forward check assumes that in the last cycle, where check is active, we retire the k plus 1th instruction, and the kth instruction must be somewhere within this m-sized window. And with the backward check, we assume the opposite. Yeah, then the register file consistency. Liveness is just a check that there we have a trigger signal. So we have a trigger signal somewhere within this m-cycle span, and we retire an instruction k at this point where we trigger. And then somewhere else in this m-cycle span, we must see the next instruction, the instruction k plus 1. And if this fails, then either this m-cycle span is not long enough, or we have just proven that our core can just freeze, and that would be bad. There is a check to make sure that this instruction index is actually unique, that there are not two instructions with the same index in the instruction stream. And we must make sure that the reordering preserves causality, so that when we have an instruction that writes something to a register, and then another instruction that reads this result from the register, then these two instructions must be relative in order. Luckily, most cores that reorder their instructions preserve causality. But this is something that we assume in some of the other proofs, and therefore we must also check it. So what kinds of bugs can I find with this? It's hard to give a complete list of all the possible bugs that we can find. But the first one is probably the easiest one. If you just have implemented the semantics of an instruction incorrectly, then we will find it. Then bypassing forwarding bugs you can find, because that would essentially say you've written one value, but you've read a different value from the same register. When the reordering is going wrong with respect to registers, reordering with respect to memory is not checked at the moment. We can see in some cases when it freezes, this is this liveness check. However, for this, we might require so-called fairness constraints. So one possible scenario where my processor is freezing is when the memory doesn't answer a fetch request, for example. And then, of course, my core will wait forever. So we need to add an additional assumption to our proof that we say, well, the memory will always return within so many cycles. And then we can say, OK, given this fairness, we assert liveness for the core. Some bugs related to memory store, load, and fetch instructions can be found. However, this is not integrated with all cores yet. Things we can't find right now is things that's beyond the RVFI interface. So at the moment, we don't have CSR reflected in this interface, so we can't check anything with regards to that. We also don't have the floating point instructions covered yet. But there are RFCs, how we are going to extend RVFI so we can also cover this kind of stuff. The other thing that we more or less inherently, because of the case of the type of the way we handle those checks, the other thing we can't do right now is things related to concurrency and multiple hearts. But I have a good excuse here, because right now the memory model isn't frozen yet, so I wouldn't even know what to check. So the processors currently supported are my processor, Pico RV32. For this processor, the RV32IC ISA version is fully verified with this. The other thing that we have support at the moment is RISC-V Rocket. So this is under construction. The RV32I thing is more or less implemented right now, so we can check that. However, the depth of this check is not as good as I wanted yet. We still need to do some things with abstractions. And support for 64 bits is underway for this as well. RISC-V formal would support RV32IC already. I have it here. but the RVFI interface for RISC-V Rocket is not there yet. So these are the cores. If you want to add support for your own core, just add a new directory under riscv-formal cores. Then write a wrapper module that instantiates your core and all necessary peripherals for your core or abstractions of that peripheral. So usually that's just some kind of memory thing, memory mockup. Then you need to write a configuration file that tells riscv-formal all the things it needs to know about your core. And when you have done that, you can run the checks generator, and it will create a directory with all the configuration files for Symbiosis, and then you can just run Symbiosis for all the things there. And either enjoy your fully verified processor or spend days looking at counterexamples that are really, really strange. I've mentioned abstractions a few times. I think I should mention what they actually are. There are three terms: cut points, black boxes, and abstractions. And all of those cut points and black boxes, they are also abstractions. And cut points are probably the easiest abstractions. So I take my design, and I pick a wire in my design, and I disconnect the driver from the wire. And instead, I make this wire completely unconstrained, and it can have any value at any point in time. And if my check still succeeds after this modification, then obviously it must also succeed with the original driver, because the completely unconstrained wire can't do anything that the original driver would have done. So it's a more general proof. However, it might also be a simpler proof, because now I don't need the driver anymore, and I can optimize away a large chunk of my design, or a small chunk, depends on what kind of wire I just cut. Black boxing is exactly the same thing, except I do it for all the outputs of a hierarchical instance. And then I can, by definition, throw this entire hierarchy that I black boxed out. So these are the two simplest abstractions, but there are other abstractions. So anything where I change the design to make the proof easier, or in the hope to make the proof easier, where I make my design more general, is an abstraction. So the classical textbook example would be, I have a counter that just increments in each time step, and I replace that counter with an unconstrained wire, and then I add this additional constraint, this assumption that I say the counter right now must be greater than the counter in the last value, at the last time step. And of course, a counter that increments in each time step satisfies this criteria. But now, suddenly, the counter can also jump 100 steps or whatever, so we have a more general circuit. And maybe that's a counter that's waiting for some kind of initialization to finish. And usually, I would have had to run a bounded model check with a really, really large depth, because I would have needed to wait for this counter to reach a certain threshold. And now it can just jump over the entire range it would have counted. Another example would be an ALU-like circuit that has like input values and an output value, and something that selects an operation. And we only implement one of those operations. And for all other operations, the output is completely unconstrained. That would also be an abstraction. So within riscv-formal, abstractions can be used a lot, because I have all these small individual checks. So when you consider, for example, the instruction checker, it only looks at the very, very last instruction and the value that was read from the register file and the value it will write to the register file. It doesn't check if the value we have read from the register file makes any sense in the context of the instructions that were retired before that. So with an instruction checker, I can just completely black box the entire register file. And that will hopefully make the proof a little bit easier. And I can also add cut points for all the bypassing paths I have in my design. On the other hand, when I look at the consistency checker doesn't care if the ALU actually implements the operation correct for each and every individual instruction. It only checks if the value written to a register file by one instruction, for example, is consistent with the value read later on. So for this kind of checks, we can disable the ALU. And for some other checks, like this program counter forward-backward checks, we can also black box the register file again. And you can see, if I would have one large proof for everything that makes up the riscv-formal specification, I couldn't black box anything, because hopefully everything in your core is actually important to implement the desired behavior of the core. But because I've split it down into these small individual proofs, in each of those proofs there are some things that I can black box and make the proof much, much easier. However, when we do these abstractions, there's one thing to keep in mind, that there are two effects an abstraction can have. And the first one is that the proof just becomes easier because I don't need to consider a certain part of the design anymore. However, now it's possible that with the same bounded model check depth, I can reach a much, much wider state space within my design. And that can actually make the proof harder because I'm, for example, still running something that's 10 steps deep, but suddenly it has the same complexity like something that's 100 steps deep because I can reach all possible states in the design at once. And because of that, it's possible that you add an abstraction, and it's a very useful abstraction. You should use this abstraction, but the proof that previously succeeded in like 2 hours doesn't succeed anymore. And what you have to do is actually decrease the bound of your check to make it work again. So this raises the question, how do we find out what bounds are good for this kind of stuff? And the problem, of course, is if it's too deep, then it won't finish in any reasonable amount of time. And it's too shallow, then maybe I might miss something that's important, and I might miss a bug. The solution is to use formal cover statements. So I make a separate formal proof, a formal check, that just says I'm interested in this kind of things happening with my core. And then it will find out for how many cycles I need to run the core at least for these things to happen. And this gives me a better confidence that if I do, for example, a bounded model check with 30 steps, and I can reach all my cover statements within 30 steps, then I have a much higher confidence that actually 30 steps is a really, really good depth, and I can reach a lot of the important design space within that bound. In some cases, you might even need to further duplicate checks and like run something with all the abstractions enabled, but very shallow, only 10 cycles maybe, and then run another check with all the abstractions disabled and maybe 50 cycles. And those two things combined give you the confidence that you actually have covered all the ground that you would like to cover. So future work for this, I would like to support more ISA extensions. So the next stuff is the floating point stuff and multiply and 64-bit. Also, I would like to support CSIs. Both require extensions to this interface, but there are already RFCs how I would like to do that. I would like to support more cores, but slowly, not everything at once, because the more cores I have in there, the harder it will be for me to change any of the interfaces. But if you think this is awesome and you would like to be a part of it, and you happen to have a RISC-V core, and you want your RISC-V core to be the next one supported here, please talk to me. Yeah, and also better integration with non-free tools, maybe, if I have the time for that. OK, thanks. Are there any questions?
Really nice work. How do you handle things where operations get optimized out? So, for example, if you had a sequence where you write to a register, read from that register, the value isn't live anymore, and you write to that register again, and you decided to make that first write not appear to your. I mean, it didn't go to the register file. It went through the result forwarding network and ceased to be. In that example, would you report that as a failure because you missed the commit of that instruction?
I would say the riscv-formal interface doesn't really cover that yet, because what we would need for this is for the write register also a flag that essentially says ignore the value that was written and just make sure nobody will ever depend on that value or something like that. However, that shifts the problem, because now if you have like 2 instructions,
I mean,
yeah, but
if it has to do with what's the observable state of the machine. If you can't interrupt it at that point because maybe you've interlocked it because you're doing this trick, just as an example, then it would never be observable that write
in this case, you would retire it as a fused instruction.
I see.
And then, so right now we don't really have support for cores with fuse instructions, but in my mind I know how to implement them. And possibly we need another read port and maybe even a second write port. But in this case, with fused instructions, you often have something like the destination register of the first instruction is the same as the second instruction, and the fused instruction does only have one destination register.
It might be necessary in the model to say there's a register right here that actually didn't happen in the actual hardware. And I like the way that you would also handled out of order retirement when the core decides it's safe to do that.
Yeah.
So that's very nice. Thank you.
Okay. If you have any more questions, just find me and we chat. Thank you.